How perfect conditions create monsters. Every tornado begins with a recipe. Warm, moist air at the surface, cool, dry air above, and wind shear. A change in wind speed or direction with height. When these ingredients mix, they can form supercells, the rotating thunderstorms that produce the world's most violent tornadoes. In late May 2013, the southern plains were primed. Warm, humid air from the Gulf of Mexico clashed with cold, descending air from the Rocky Mountains. The jet stream overhead provided the spin. Meteorologists at the National Weather Service, NWS, had issued a particularly dangerous situation, PDS, tornado watch early that afternoon, warning that conditions could produce long-track violent tornadoes. No one could have guessed just how violent. The birth of the El Reno tornado. At 6:03 p.m. local time, a rotating wall cloud developed southwest of El Reno. Within minutes, radar confirmed that a large tornado had touched down in open fields. Spotters reported multiple vortices swirling around a massive central circulation, an ominous sign of a rapidly intensifying storm. As it grew, the tornado's internal structure evolved into what scientists call a multivortex system. Several smaller tornadoes orbiting within a larger, rotating parent circulation. Each of these subvortices carried winds exceeding 300 miles per hour, 480 kilometers per hour, though the broader tornado's official maximum sustained winds were estimated near 296 miles per hour. By 6:28 p.m., the tornado reached its maximum width of 2.6 miles, wider than the entire city of Manhattan, New York. Imagine standing in an open field and seeing the horizon itself rotate. That's what El Reno faced, the chaotic beauty of a giant. Unlike the classic cone-shaped tornadoes seen in movies, the El Reno tornado was a sprawling, amorphous wall of rotating air, more like a moving thunderhead scraping the ground. Eyewitnesses later said it was nearly impossible to tell where the tornado began or ended. The sky itself seemed to spin. Chasers who pursued it, including seasoned meteorologists and documentary teams, described seeing multiple funnels weaving in and out of the main circulation. The storm's immense width meant that wind speeds and directions varied wildly from one side to the other. In some places, calm air existed only a few hundred meters from total devastation. Lightning flashed inside the dark core like a heartbeat, illuminating shredded trees, overturned vehicles, and streaks of debris whipping through the air. For scientists, it was both mesmerizing and horrifying. A once-in-a-generation event revealing the atmosphere's raw mechanics. The human story, tragedy, and survival. El Reno's residents had been on high alert. The deadly Moore tornado just 11 days earlier had killed 24 people only 20 miles away. When sirens sounded again, many fled their homes, creating traffic jams on the city's highways. Some storm chasers, professionals who normally observe from safe distances, were caught off guard by the tornado's rapid expansion and erratic motion. Among the victims was Tim Samaras, a world-renowned storm researcher featured on Discovery Channel's Storm Chasers. Tim, his son Paul, and colleague Carl Young were killed when the tornado abruptly changed direction. Their deaths marked the first time professional storm chasers had been killed by the storms they studied, underscoring just how unpredictable this monster was. Dozens of vehicles were thrown hundreds of yards. A semi-truck was found twisted around a tree. Yet remarkably, much of the tornado's path remained over rural farmland, sparing El Reno from a catastrophe on the scale of Moore or Joplin. The science behind the record. The 2.6-mile width of the El Reno tornado wasn't measured by guesswork. It came from mobile Doppler radar units capable of mapping wind speeds and structure in exquisite detail. The University of Oklahoma's Raxpol radar recorded the storm's outer boundaries as they swept across open terrain. Meteorologist Dr. Howie Bluestein described it as an almost surreal radar signature, an enormous donut of rotation. These measurements gave researchers new insights into how tornadoes expand and contract, often within minutes. Interestingly, while the El Reno tornado was the largest ever measured, it was later downgraded from an EF5 to an EF3 on the enhanced Fujita scale, because the areas it struck didn't have many strong structures to analyze for damage. The EF rating measures intensity based on destruction, not wind speed. meaning this colossal storm likely produced EF5 winds but didn't have enough man-made targets to prove it. The multi-vortex mystery. One of the most fascinating discoveries from El Reno was its complex internal structure. The tornado contained multiple small-scale vortices spinning within the larger circulation, each capable of causing localized EF5 level damage. High-resolution radar scans revealed these subvortices rotating at speeds over 250 miles per hour, orbiting the main vortex like moons around a planet. This finding reshaped scientists' understanding of how tornadoes intensify. Instead of one coherent funnel, the El Reno tornado acted more like a chaotic cluster of smaller tornadoes merging and splitting continuously. Such structures explain why damage patterns from large tornadoes often look patchy. One house leveled, the next nearly untouched. It's a reminder that inside every tornado lies a complex ballet of atmospheric forces. Lessons learned: science, safety, and misconceptions. In the aftermath, meteorologists and emergency planners studied the El Reno event obsessively. The storm revealed how fast tornadoes can change direction and grow in size, challenging old safety rules. For instance, many people tried to outrun the tornado by car, a dangerous choice that led to traffic gridlock and several fatalities. The new recommendation: shelter in place unless a tornado is distant and you have a clear evacuation path. For scientists, the event emphasized the need for more mobile radar coverage and public education about tornado unpredictability. It also demonstrated that tornado warnings must communicate not just that a tornado exists, but how unusual or dangerous it is. What made El Reno different? Several factors set this tornado apart. Sheer size. At 2.6 miles wide, its base covered an area larger than most entire towns. Rapid growth. It expanded from a small funnel to its record width in less than 30 minutes. Erratic movement. The storm made sudden direction shifts, catching even experts off guard. Unprecedented data. Mobile radars captured every stage, making it the most thoroughly studied tornado in history. The storm's chaotic nature also blurred the line between a tornado and a mesocyclone. Some researchers debated whether it was truly a single tornado or a cluster of overlapping vortices functioning as one. Regardless, the data gathered has since influenced tornado modeling, forecasting, and emergency response protocols worldwide. How the record stands today. As of 2025, no tornado has surpassed El Reno's 2.6-mile width. Other powerful storms, such as the 2011 Joplin tornado and the 2013 Moore tornado, caused more fatalities and destruction, but none matched El Reno's sheer scale. Researchers continue to analyze its data using machine learning and high-resolution simulations. These studies have improved tornado genesis prediction, potentially increasing future warning lead times from minutes to tens of minutes. A life-saving difference. The event also accelerated the integration of dual polarization radar and mobile data networks, helping meteorologists understand not just where a tornado is, but what kind of debris it's lifting, revealing its intensity in real time.